record. And let's get started. So I think I left you with a little bit of an exercise last time. And that exercise is basically to show that the measure of any finite set is 0. That's not an if and only if, right? It was an if and only if, I probably would have stated it as such, or I would have, told you, hey, this is an if and only if, even if we can't prove one of the directions, that's fine. So yeah, let's write it out. So I guess I called this a proposition, I think. So proposition, any finite set has measure 0. Okay, again, not all if and only if, there are infinite sets that will also have measure 0. In fact, I'm probably going to make you do an example of one at some point. All right, so let's, I literally just fixed the pen. Okay, there we go. Not solution, this is a proof. All right, we're gonna do this by induction, right? As you should, with oftentimes when you're doing things on finite sets. So let's begin by, in this case, I don't think the empty set is our base case because it's kind of silly. So let's do the single set as our base case, so the singleton set. So let S consist of a single point, be the singleton. Okay, now we argued, did I argue this? Oh shoot, you know what? I actually might need a result before this. Here, let me just, let me throw this claim in here real quick. We'll do it as part of this proof. So claim, if the outer measure of S equals 0, then S is measurable. And the measure of S is 0. Okay, so I'm not saying for the singleton set, I'm saying, yeah, exactly. And I realize I think I need, yeah, okay, if I didn't state that, then I'm going to do the claim. So I'm going to prove the claim first. And this is not for the singleton set, this is for any set. So for any set, if you show that the outer measure is 0, then S is measurable and its measure is 0. Okay, so the proof of that claim is pretty easy. Pen. Right? So the measure has to always be non-negative. Okay, that's pretty easy to check because the measure of any polyrectangles that you have is always non-negative, and then you're going to take an infimum of them. So the worst you can do is be equal to 0, right? The inner measure is always less than the outer measure, but the outer measure is also 0. So you get some sort of like squeeze theorem thing happening here, and it forces the inner and outer measures to be equal and equal to 0. Right? So the inner measure equals the outer measure equals 0. Okay, so there isn't much to that. That one's pretty straightforward, but again, we're just going to need that for this whole thing, because basically instead of doing, making some arguments about inner and outer measure, we're just going to talk about the outer measure, and we're just going to show the outer measure is 0. Okay, so that's our goal. So S, let's return back to the main proof. Okay, so S equals just the singleton P. So that is our set. Let's show it has measure 0. And the way that you show, again, that a set has measure 0 is you show the following. So we want to show that for all epsilon, right, there exists a polyrectangle. What is going on, pen? So we want to show that for all epsilon, right, we're going to use the epsilon definition of the infimum. So for all epsilon, there exists a polyrectangle, or polyinterval, I've been calling them, polyinterval, such that 0 is less than or equal to measure of P is less than epsilon. Okay? And again, you might be like, wait a second, that doesn't look like the epsilon delta definition of the infimum, or the epsilon definition of the infimum. But again, just kind of maybe let me put this, right? Normally, this is what we would have done. But in this case, that outer measure we're claiming is 0, right? So if we replace mu upper star S with 0, we do get the statement above. So if you're kind of like, wait, why is that the thing that we're trying to do? The thing in yellow is the epsilon definition of the infimum. And if we plug in 0 everywhere, that's what we get, right? So we basically, and if you think about this intuitively, it makes sense. What are you trying to show? You're trying to show that there's a covering polyrectangle, a rectangle which covers your set, which has arbitrarily small area, which, right? Arbitrarily small length. And if you can do that, then yeah, the infimum of those things should be equal to 0. So hopefully that makes sense. And we have our singleton, right? Just equal to P. So let's say let P, big P, be equal to little p minus epsilon over 4 to P plus epsilon over 4, like that, right? That's a very simple Pauli interval. It's really just an interval, right? It's not even a disjoint union of intervals. So this is a Pauli interval, and its length is epsilon over 2. So S is contained in P, and the length of P is epsilon over 2, which is less than epsilon as required. Okay. So singleton sets are measure 0, right? You can definitely cover them with polyrectangles, which are, or poly intervals, which are arbitrarily small. Now you can imagine if you wanted to do it for a finite set, you actually could have gone just straight to the answer, right? You could have just, really you should do it by induction, but you could have just said, let S be P1 ... Pn, right? A collection of finitely many points, and then, put really small intervals around it, everything. I think it's easier to do with induction. So we're going to do it with induction. So now assume, so inductively, we're going to assume any set with k minus 1 elements has measure 0. And let's take our set now to have k elements, pk. Okay. And the natural thing to do here is to split S up into a set with k minus 1 elements and 1 element. P k minus 1 union pk, right? Let's call this thing, let's call that S1. And we'll call this thing S2, something like that. Okay, now by our induction hypothesis, S1 has measure 0. So by our induction hypothesis, the measure of S1 equals 0. So there is a polyrectangle or polyinterval. So there is a polyinterval P1 such that it covers S1. And I guess we should let epsilon greater than 0 be given. Whatever, it's there. And what do we want? 0 is less than equal to the norm of P1. And what do we want? Let's do epsilon over 4 here or something. Do I need epsilon over 4? We could probably do epsilon over 2. Okay. If we need to make the epsilon smaller, we'll go back and we'll do it at the end. All right, so that covers, right? This is us using our induction hypothesis. We've got these k minus 1 elements in S1, cover them with a polyrectangle that we can make arbitrarily small. Obviously, we can cover S2 with a really small polyrectangle too. So let's do that. So let capital P2 be pk minus, what do we want here? Let's do epsilon over 8 just to be safe. It's probably too small, but who cares? So P2 covers S2, and the length of P2 is epsilon over 4, which is less than epsilon over 2, right? The only thing we have to worry about, there's just one little thing that we have to worry about here. So obviously what I want to do now is I want to take the union of P1 and P2, right? And then make some sort of argument that the length of this new polyinterval, once I've unioned these two things together, that their union has length, which is at most the sum of the measures of the two polyintervals. Strictly speaking, though, if I want their union to be a polyinterval, I need to make sure that they're disjoint, right? So rather than go through a long technical argument, I think it's fine for you at this point if you want to just say, let's wave our hands. And let's say, yeah, I mean, you can obviously shrink P1 if you want, or P2 if you want, to make sure that they're disjoint. So let's just assume that you can do that, right? So if necessary, actually what I would do, I would shrink P1. Because you said explicitly what P2 is, so you don't want to like set it explicitly and then say, well, shrink it, if you want. P1, we said there is a P1 which exists, and we can certainly take it to be smaller, right? So if necessary, shrink P1 so that P1 intersect P2 is disjoint, right? Is empty. Therefore, now when I union them, I do get a polyinterval. Now P1 union P2 is a polyinterval. And P1, its length is its sum. Okay, we haven't formally proven this. It's a very easy proof though, right? Like if you union two polyintervals, those polyintervals are disjoint. Well, then the length of their union is the sum of their lengths. Very straightforward proof, right? It's just almost by definition, because each of them are just made up of a disjoint union of intervals. You union them together, boom, you still have a disjoint union of intervals. What is the length? Oh, it's the sum of the lengths of each of its constituent intervals. Yeah, you're done, right? So it's very easy proof if you want. And S equals S1 union S2 is contained in P1 union P2. Hence, we have 0 is less than equal to P1 union P2 is less than epsilon over 2 plus epsilon over 2 equals epsilon. So the measure of S is 0. And so we're done, right? Because again, by the blue claim that was above, we only need to show the outer measure is 0. And if we do that, boom, we're done. Okay. So again, the idea here is that, as I've kind of been saying, this proof isn't bad. It's kind of intuitively what you would expect to be true. But often these sorts of proofs just end up getting stretched out a little bit just by virtue of the fact that, yeah, there can be a little bit technical. And that's what I was saying about integration, right? Usually the ideas aren't terribly tricky. It's just that actually writing them all down and making everything work, because you're constantly playing around with epsilons, right? It's quite messy. It's unavoidable though, right? There's nothing really we can do about that. And this is analysis in general. I always say like the key part of analysis is just, hey, there's some points which really are badly behaved, and you put them in little epsilon prisons, and then you do, you prove your theorem away from the bad points, and then you argue that you can squeeze the bad points to death by making epsilon get really, really small. And that's a lot of analysis in a nutshell. That's like 80% of analysis. And obviously, that gets complicated as you get more and more sophisticated, but underneath the surface, in my opinion, that's morally what's always happening. Okay, any questions about this? This stuff can be a little bit annoying too. Like you'll probably notice that I'm not proving all the claims. So for example, I didn't prove this one. And it's because some of these are just are tedious and in some sense obvious. So if you're really upset, you can try them yourself. Is there another one that I made that I didn't prove? I think right now that's it. But yeah, some of these things I'm just going to be like, check it yourself, just because, again, if we spent class time on it, we would just get bogged down in detail. If you ever go take like a hardcore like third-year analysis class, they'll do all the details. And then your brain will rot because you'll just be so bored. Unless you enjoy this stuff. Maybe you do. Okay. All right, let's do another proposition. Maybe this one should be a theorem, but we'll find out. So let's begin by supposing that we have two measurable sets. Okay, so we're gonna rattle off like 5 results that are true. So 1, if S1 is a subset of S2, then the measure of S1 is less than or equal to the measure of S2. That seems like a pretty easy consequence from the thing that we proved on Tuesday, right? This one is easy. Okay, you should try it yourself, but this one's pretty straightforward. 2, so the measure of S1 union S2 is less than or equal to, oh, maybe I should state this one first then if I want to do this. S1 union S2 and S1 intersect S2 are measurable. Okay, so unions and intersections of measurable sets are measurable. The other thing too immediately is if you get it for 2 sets, then you immediately get it for any finite union or finite intersection, right? Because you would just prove it by induction. So you know that S1 is measurable, you know the union of 2 sets is measurable. As an inductive hypothesis, suppose that the union of K sets is measurable. And then when you do K plus 1, you do exactly basically the inductive step that we did before, break it into K sets and your extra set, smush them together. Their union is now measurable, everybody wins, right? So implicitly, I'm not going to say it, but you can now prove that, yeah, if you know that 2 sets is measurable, it's true for any finite combination. I can say this one's in the intermediate hard range. It's definitely doable. You don't need any tricks or anything to do it, but it's a little bit tricky. Okay, so the measure of the union is, so we say here that the measure is subadditive. So it's not equal. The best we can do is less than or equal to, right? And really the problem here is that S1 and S2 could overlap. There's nothing here saying that S1 and S2 have to be disjoint. If you assume that they are disjoint, then the measure is in fact additive, right? So as long as S1 and S2 don't intersect, then it turns out that the measures are equal. We're not going to care about that, but if you want to prove it, you can. This one's fairly easy-ish. Okay, it's basically just an example of define, like, again, use the outer measure. Try and use the outer measure whenever possible. Avoid using the inner measure. Inner measure is not nice. Use the outer measure, and S1 and S2 are both measurable. Again, argue that when you union them, you can basically union them with a Pauli interval, which covers their union, that sort of thing, right? 3, if S, or let's say if A is a real number, and we define S plus A to be X plus A, where X is an S. Okay, so basically you just took the whole set and you moved it left or right by A units. Then S plus A is measurable. I guess S1, let's call it S1 because we didn't just have an S. And their measure does not change. Right? So again, this should be intuitive. If I give you a blob and you know what the length of that blob is, and then you take it and you just shift it 10 units to the right, well, you haven't really changed anything. You just changed where on the real line it occurred. You haven't structurally changed its length at all, right? Or its area or its volume, if you want to think about it like that. You haven't changed its size. You haven't scaled it or anything. You just moved it around in the interval. Its area shouldn't change, right? That's what that says. And then 5, and this is the fun one. And oh yeah, how hard is this one? This one, yeah, this one's pretty easy. And then this one that I'm about to do is, I'd say, intermediate, and that's the one I'm going to prove. So if we define this thing, let's do A. So T here is the scaling map, right? So T takes a number and multiplies it by A. So this is the scaling map. Then what we would expect is that the measure should scale as well, right? So if I take an interval and I triple it, right? I scale it by 3 by multiplying everything by 3, then we expect the measure to increase by 3 as well. And of course, in this case, we use the absolute value of A, because if you use negative A, it does scale it, but it could actually, pop it onto the other side of the, I don't want to say y-axis because we're not thinking about this in 2 dimensions, but it could throw it into the negatives, right? So if it ends up being a positive thing, it ends up doing this reflection. And so we just have to be careful about that. And we're interested in the absolute value of A. Those of you who are taking linear algebra this term, when you do this in higher dimensions, what you do is you don't actually have a scaling map anymore. You have a linear transformation, and then the thing you scale by is actually the determinant. And there's a real sense in which that's the definition of the determinant. So if you haven't seen the determinant yet, don't worry about it. If you have, basically, you put the determinant here. And the determinant of this map is linear, and its determinant is, A. But yeah, when you do this in multiple dimensions, you scale by the determinant, and that is what the determinant is. So depending on whether, Asan or whoever, if you're taking 223, whoever teaches you linear algebra, when you learn about the determinant, that's really what's going on. Okay, the determinant tells you how volumes change. Okay, so I'm going to skip most of these, especially since most of them are easy-ish. So again, maybe this last one, this is just kind of intermediate. So I'm going to do 5. Okay, I'm going to leave the rest for you. The only one I'd say, again, here is kind of tricky is probably number 2. Oh, did you? No, but Anika, you heard determinant, right? You like that word should have showed up. Right, okay. So yeah, the problem with the determinant is, so there's a bunch of ways you can define it, right? And what you probably saw was just the computational definition where you take like, what is it, the Lagrange expansion, yeah, AD minus BC, or this like alternating sum of the minors, right? The cofactor expansion of the determinant, which is computational and fine, that's okay. And in practice, if you compute a determinant, that's the best way to do it. But what is it like? What does it represent? And what you learn is that the determinant, for example, gives you some sort of condition on non-invertibility. That's great too. It definitely does do that. But when you ask, that condition seems too coarse. Like you're invertible if your determinant is non-zero. Okay, but is there a difference between a linear transformation that has determinant 7 and one that has determinant 50? Like, are the only thing we care about is that it's non-zero, or do those numbers mean something? And the answer is those numbers do actually mean something. And what they mean is precisely by how much your linear transformation changes the volume of the thing that you're working on, right? So that's really what the determinant is capturing. There's another way, which is a super cool way of doing it, but is way too advanced, even for like 240 or 247, which is basically to every vector space, there's like a one-dimensional analog of it, which is basically you take a wedge of it together as many times as equal to its dimension, and that's complicated. And then there's this perfect correspondence between linear transformations on your original space and linear transformations on your new space. And you can show that linear transformations on your new space all have a certain form, and the determinant pops up there very naturally. And if you want to prove things, that's definitely the best way of doing anything, that definition. But that one's too hard for anyone who isn't probably a grad student. There might be a better. Yeah, you need multilinear algebra. So you at least have to have taken like 257 to see that definition. Okay, so yeah, the only one here, I do expect you to be able to do 1, 3, and 4 on your own, especially once you've seen me do 5. Like right now, you haven't seen it, so you might not know how to do. The only thing here might be a little bit tough is number 2, okay? You should still try it though. See if you can do it. It's a tough one though. Okay, so what you're going to learn here is, again, like anything, it's pretty hard to work with the measure itself, right? You kind of have to work with the Pauli intervals that define the measure. So what we're going to do is basically prove that this theorem is true with Pauli intervals. And when you want to prove it's true with Pauli intervals, the best thing to do is to start with intervals, right? So if I already used A, damn it. Okay, whatever. I have to live with I made my bed, now I have to sleep in it. So if BC is an interval, then the image of BC is equal to either AB, AC, right? So that's if A is greater than 0, or AC, AB, if A is, let's say A is greater than or equal to 0. Okay, so this is just always true. Okay, now notice in both of these cases, though, the length of that interval. So we're saying, first of all, the measure or the image of intervals is an interval. That's great. And then if we actually take a look at what the measure of this thing is, or the length, because this is an interval, and the length of TBC is therefore always equal to, so it's going to be equal to what? AC minus AB, right? If A is greater than or equal to 0, AB minus AC, if A is less than 0. Very convenient. That is exactly the definition of the absolute value. Right? And so our notation is very nice for that reason. So basically we get that the result holds on just intervals, right? Now, Pauli intervals are disjoint unions of intervals, and images can't map disjoint things to non-disjoint things. Well, let me double check that. I mean, it can, but not in R. Let me just double check. Yeah, they can, but yeah, actually, let's just double check this. They can map non-disjoint things to non-disjoint things. No, but linear ones can't, right? That's the point. Linear maps can't. So since T is linear, it preserves disjointness. Right? And by this, what I mean is C, B not, yeah, exactly. Yeah, I didn't put it in absolute. You could put it in absolute value certainly if you wanted, but we already know that C is bigger than B just by virtue of how we define intervals. So we already know it's bigger and we're not worried about it. Actually, I guess here our definition uses like, we don't use square brackets in our definition. We do in 257. So my brain is a little bit screwed up there. But yeah, sorry, these should be non-square brackets. Right? But exactly, we already know that C is bigger than B, so we're good. Okay, since T is linear, it preserves disjointness, i.e. if two sets are disjoint, then their image under T must also be disjoint. So if A intersect B is disjoint, then TA intersect B is also disjoint, right? Because the only thing it can do is scale. And if the only thing it can do is scale things, then if you started being disjoint, you have to end up disjoint. Again, you can prove this formally if you want, or you can just take my word for it. This is not true of arbitrary functions. Arbitrary functions can definitely map, disjoint sets to non-disjoint sets, but because this map is linear, it can't violate disjointness. Again, all it does is scale, right? Okay, so basically, because it scales intervals exactly the way we want to, and it preserves disjointness, this means that this the result that we want to be true for Pauli intervals is true, right? Right. So thus, if P, let's say I1 union ... union IN, is a polyinterval, then, and remember, so those i's are disjoint, right? Then T of P is equal to Ti1 union dot 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 union Tin is also a polyinterval. And its length, because disjointness is preserved, is just the sum of these things. And each of those is just what it should be, because we proved the result on intervals. And then if we factor the A out, well, that sum of the lengths of the intervals is exactly the length of P, right? So great, we now have the result on polyintervals. So now we just need to say, well, if it holds for every polynomial, it must hold for the measure as well, right? So this is going to take a little bit to do, but that's the rough idea. Okay, so first thing we have to do is we have to prove T is measurable. All right, so claim T of S is measurable. Okay, so let's prove this. So I'm going to make another claim here that I'm not going to prove, but hopefully you believe it. So it suffices to show that there are polyintervals I'm going to call them P hat and Q hat, such that P hat is a subset of T of S, subset of Q hat, and this is true, right? So this is, again, I don't want to prove this. It does take a little bit to prove, but we've basically already proven this, right? When we were talking about, remember, in the definition of integrability, we said the interval the integral is precisely the number which is between the infimum of the upper sums and the supremum of the lower sums. If you think about the P hats here, right? So the polyrectangles or polyintervals that live inside of T of S as being the under approximations, right? Like the lower sums, the inner measure is their supremum. And if you think about the Q hats, the over approximations, as being like the upper sums, their infimum, right, is going to shrink down as well. So our definition of integrability is basically this. And then from that, we proved that the sups of the under approximations was equal to the inf of the over approximations. And that's precisely the statement that the inner measure is equal to the outer measure. Okay, so it might be worthwhile just kind of proving something like that in general, but hopefully you believe this. And if not, spend some time to prove it. And if you don't remember exactly how I proved that for upper and lower sums, go back and double check it, okay? Okay, so to show that it's measurable, it suffices to prove this. Now, what are we going to do? So we know S is measurable. Right? So in particular, we can find, polyintervals which do this for S. So there exists P and Q with P subset S subset Q. Oh, you know what? I should have said if C equals 0, there's nothing to do. Let me put that in. All right, so if C equals 0, then T of S is just the set 0, which is measurable, right? So otherwise, so suppose C is not 0. That way I can divide by it here. Okay, always one of these stupid little cases where you have to think of the empty set or something. Okay, so now I'm going to let P hat equal T of P and Q hat equal T of Q, which will give us, right, because we've got this chain of subset inequalities here. So that will give us T of P equals P hat is a subset of T of S is a subset of Q hat, which is T of Q, right? And we'll have that the difference between these two things, again, these are polyrectangles, and Q hat is equal to T of Q. So this is going to be A times, oh, sorry, it should be A, not C. A times Q minus A times P, which is equal to A times Q minus P, which is equal less than A times epsilon over A, which is equal to epsilon, and so we're done. Okay, all right, we're just about done. So now we know that the image set is measurable. Now we just need to show that it is what we want it to be. All right, so now claim. We're just about done that the measure of T of S. So now this makes sense, and we can even write it down, is equal to A times the measure of S. Okay, for this, once again, let's do the A equals 0 case right now. So if A equals 0, then we're going to get the measure of T of S is just the measure of the set 0 is equal to 0. And yeah, that's going to be equal to the absolute value of 0 times the measure of S. So we're done. So assume A is not 0. Okay. Now, since we know that both sets are measurable, we don't have to prove it for both the inner and outer measure. It actually suffices just to prove the result for the outer measure, because the outer measure is equal to the measure, right? Because both sets are measurable. So it suffices to show that the outer measure of T of S is A times the outer measure of S, i.e., for every epsilon greater than 0, there exists a partition containing S, or a polyinterval, sorry, containing S such that, okay, so what are we doing here? So the outer measure is the inf of the over approximations, right? So if I've got the inf, then there's something between the infimum and the infimum plus epsilon, right? So we want the A times the outer measure of S plus epsilon is less than, but wait, which side is this? So I've got the inf plus epsilon, and there's something in between there, right? So that's got to be the other side. So I've got measure star of S is less than or equal to P is less than A times the outer measure of S plus epsilon, right? Because I'm doing the infimum, so I want to go forward. Okay. Now, as usual, what I'm going to do is use the fact that, oh, maybe let me call this P hat, just because that's what we've been doing for, oh, and I wanted to contain T of S. Okay. So again, this is, let me show you here. So what I would normally do is I would actually, right, I'm trying to do the measure of T of S. So normally this equation would look like this. Right? So this is normally how this equation would look for the outer measure of the image of S. But I'm trying to prove that the absolute value of A times the outer measure of S is this thing, right? And this is the definition of what it means to be the infimum. So if I can prove that the absolute value of A times the measure of S satisfies this property for any epsilon, then those two things have to be equal, right? There's only one number which does this, and it's precisely the infimum of the over approximating polyintervals. So if we can prove that the absolute value of A times the measure of S is the thing which does this, then these two things have to be equal. Okay, so that's what we're going to do. And again, we're going to use the fact that S is measurable. So since S is measurable, or let's say again, let epsilon greater than 0 be given. So let epsilon greater than 0 be given. So since S is measurable, there exists a P containing S such that mu star S is less than or equal to P less than or sorry, strictly less than mu star S plus epsilon divided by that, right? And then basically what I'm going to do is, again, I'm going to say let P hat be T of P. So that we're going to have, so basically what I'm going to do, let me maybe label this equation so that multiplying 1 by the absolute value of A gives what? So it's going to give us A mu star S is less than or equal to A times P, which is less than A times mu star S plus epsilon. And this thing right here, that is exactly the length of P hat, right? So we're done. And that finishes the whole proof. Okay, so I strongly suspect that people are dying, right? And again, it's that, well, how long is this proof? Oh my goodness, it's so long. All right, so people are dying. This is, again, one of those things where it's just like, I hope you believe that none of these, so the hard proof is harder, right? The easy proofs, when I say proofs are easy, they should be like here, right? So the cutoff would be like here in terms of writing. So that would be the easy things. The intermediate is a little bit longer and the hard is a little bit longer. Actually, I'd say the hard proof's probably about the same length, but it requires a trick. So it actually does require a trick, and there's kind of nothing we can do to avoid that. So, but what I want you to do is just think about like what the process here is, okay? Because what I'm trying to say is that there was nothing kind of scary about what we did. So as a program, let's think about what we did. And then I want you to be convinced that, or I hope that you're convinced that the program wasn't hard, right? So the program, again, so we wanted to show that the measure of the image was equal to A times the measure of S, right? So what did we do? One, show it's true for rectangles. Or for intervals. Right? That's reasonable. Two, show it's true for polyintervals. Right? Three, show T of S is measurable so that we can even make sense of this. Right? Because if we don't know that T of S is measurable, even writing, this down doesn't make any sense. And then four, use the result on polyintervals to prove the result. Right? And again, so that was the program, right? Those were the 4 steps that we took in order to prove this. And I don't think that any of those individual steps, first of all, is scary. Hopefully you look at this and you're like, yeah, that seems like the right thing to do, right? The measure is defined in terms of polyintervals. We should prove it in terms of polyintervals. Polyintervals are defined in terms of intervals. Okay, that's where we should start. So we prove it for polyintervals, and then we basically prove the result. And that none of these 4 steps is extraordinarily hard. It's just that if you've been trying to keep track of this proof when we're just flying through all 4 steps, that's, I think, when you start to die. But, again, think about, hopefully you look at this program and you're like, yes, that's reasonable. And then hopefully you look at each step and you're like, yeah, I could probably do each of those. Like, none of those is too terrible. And then again, I think the death comes from trying to assimilate all of that at the same time, right? So does that make sense? Like, does the program make sense? And this is what it is, right? Like, this is what the reason why I really want to emphasize this is because so much of the integration chapter is this, where you can't prove anything directly because everything's defined in terms of sup and inf. So you have to prove it on the thing that you're suping and infing, right? So for the most part, that's going to be like upper sums, lower sums, over approximating polyintervals, under approximating polyintervals. So you have to prove it on those things, and then you have to make a sup-inf argument in order to translate it from that thing to the integral or to the measure, right, as the case might be. So it ends up getting a little bit long, right, and ends up getting a little bit technical. But the idea is that it's a multi-step process, and none of those steps are supposed to be particularly scary, right? So that's the idea, and you really have to keep that in mind and internalize that, because I don't think we had that issue when we were doing differentiation, right? Things were usually you could kind of go straight to it, but here things are just longer because they're more technical. Yeah, like, okay, what do I want to say? This proof is worth thinking about and understanding where it comes from. Like, I wouldn't worry too much about the details. I want you to kind of see like the overarching picture. Okay, so if there's a couple things that you take from this, one, I want it to be, how do I set up a program? Like, how do I think about what steps that I need? Because our proofs now are all going to be multiple steps, right? For the rest of the year, it's all multiple step things. The proofs are going to get longer. So how do you set that up? And then 2, how do you play around with sups and infs? So we've done a little bit of this when we were talking about integration. Same thing here, sups and infs are involved. How do you manipulate those in order to get what you want, right? How do I go from talking about the fundamental object, in this case, the polyinterval, to the measure? And same thing with integration. How do I go from the upper and lower sum and making claims about the upper and lower sums to making claims about the integral, right? How do you translate between those two things? Those are the lessons that I want you to take. Sure, yeah, let me try and, I'll try and do that in the future. I'll try and outline it a little bit better at the beginning so you have an idea of what we're doing. And then I'll just enumerate them off. So I can do that. At the beginning here, presumably. Yes, you are right. That should just be interval BC. Like so. Yeah, thank you, Kevin. Okay, anyway, that takes care of it today. Again, just think about it a little bit. Ideally, try and prove this one again on your own, right? Like, just look at the program and then try and replicate as much of the program as you can. And again, the way I did it isn't the only way of doing it. You definitely could find a different way. I think a really good practice for you here would try to replicate the program. And then from here, once you've done this problem, try and grind out some of the easier problems of this proposition. And if you can do that, you're in great shape. Like, there's nothing I could throw at you from a measure theory thing. Like, even ignoring number 2, the intermediate hard problem, if you can do the other 4, you're in great shape, right? So you can use that as your test to figure out, how well do I understand measure? Okay. Yes. Yeah. In terms of like measure exclusive. So as next week, we're going to talk about a bunch of things that involve measure. So obviously measure is going to pop up for that reason. Like, that's why we had to take this detour. But I'm not usually going to prove things about measure. Rather, I'm going to use things about measure. Right. So I'm going to use some of these results in order to prove things about integrals. But yeah, not too much more about measure itself. because yeah, this is not a measure theory class. Yeah, I don't want it to be a measure theory class. I hate measure theory, just FYI. But yeah, so I don't want to spend more time doing measure theory than we have to, because it sucks. It sucks a lot. Okay, that's it for us, everyone. Have a good weekend. Don't forget to work hard on your assignment. Yeah, I'll see you next week, either Tuesday or Monday, depending on whether you come to office hours. All right, thanks, everyone. Yep, see you later.